Imagine standing on the edge of a cliff. You look down and you can't see the bottom. Not because it's dark, because there are clouds between you and the ground. Now imagine someone told you, we're going to build a bridge here. Not over a river, not between two hills, over a canyon so deep, so violent with wind, so geologically unstable that engineers had nightmares about it. And then imagine that crossing it takes 2 minutes, a trip that used to take 2 hours through treacherous mountain roads. This is the Huajiang Bridge in Guizhou province, China. At 625 meters above the canyon floor, it is officially the highest bridge ever built by human hands. And once you understand how they built it, you'll question everything you thought you knew about what's possible. To understand why this bridge exists, you have to understand the land it was built on. Guizhou province in southwestern China is one of the most geographically hostile places on Earth for infrastructure. It's a landscape of karst mountains, jagged, asymmetrical limestone peaks carved over millions of years by underground rivers and erosion. For centuries, the people who lived here were essentially cut off from the rest of China, not by choice, by geography. Roads had to snake around mountains. Bridges couldn't span the gorges. They were too wide, too deep, too unstable. A journey of 50 kilometers could take an entire day. Economic growth, nearly impossible. Modern healthcare, hard to access. Tourism, forget it. This wasn't just an inconvenience, it was a generational trap, keeping millions of people locked in poverty, not because of anything they did, but because of the ground beneath their feet. China recognized this, and their solution wasn't to go around the mountains. It was to go through them and over them. Today, Guizhou is home to more than 32,000 bridges, more than almost anywhere else on Earth. But the Huajiang Bridge isn't just the biggest of them. It's an engineering statement, a declaration that no geography, no canyon, no wind, no earthquake is unconquerable. The question is, how do you even begin to build something like this? Before a single bolt was placed, engineers faced a foundational question. What kind of bridge can survive at 625 meters? At that height, you're not just dealing with gravity, you're dealing with wind speeds that can reach over 100 kilometers per hour through the canyon corridor, seismic activity from fault lines threading through the region, and uneven rock faces on either side that don't match in height or composition. A standard beam bridge would require supports in the canyon, impossible at this depth. A concrete arch? The asymmetry of the terrain made it structurally unworkable. The answer was a suspension bridge. Suspension bridges work through one elegant principle: tension. Instead of pushing weight downward through rigid supports, the deck hangs from massive steel cables, cables anchored deep into the rock on either side. The weight of the bridge, the traffic, the wind pressure, all of it is converted into pulling force, distributed across thousands of individual wire strands that make up each cable. It's the same principle that makes a spider's web stronger than steel by weight. Nature figured it out first. Engineers just scaled it up. But at 625 meters, even a suspension design pushes the limits of what's ever been attempted. Here's the problem. Nobody talks about when they show you the finished bridge. How do you build something in the middle of a canyon you can't get into? You can't set up scaffolding. There's nowhere to put it. You can't use ground-based cranes. The ground is 600 meters below. You can't even see the other side clearly through the mountain fog. The engineer's solution was to turn the construction process itself into an engineering marvel. Before anything structural could happen, engineers had to get a line across the gorge. A thin pilot cable, almost like a fishing line at this scale, was stretched from one cliff face to the other. From that pilot cable, progressively heavier cables were pulled across, until eventually a full cable crane system was operational. Essentially a zip-line highway suspended in mid-air, capable of ferrying steel components, equipment, and workers back and forth across the void. Then came something even more extraordinary. Every single steel component of this bridge, in thousands of individual pieces, was first assembled digitally. Engineers used advanced 3D modeling software to simulate the entire bridge before manufacturing began. Why? Because at this scale, a millimeter-level error compounds. A piece that's 2 millimeters off on the ground might mean a 2-meter misalignment 300 meters in the air. Virtual pre-assembly meant every component was guaranteed to fit before it ever left the factory. And then there was the matter of precision. Traditional surveying tools have limits. At extreme heights, in mountain fog, is across a 625-meter gap. Conventional measurement simply isn't accurate enough, so engineers deployed millimeter precision GPS satellite positioning, the same class of technology used in spacecraft docking, to locate every anchor point, every cable attachment, every structural node with near-perfect accuracy. The margin of error? Less than the width of your fingernail. The construction itself was only half the battle. Once built, the Huajiang Bridge would face 3 relentless enemies every single day for the rest of its existence. And the first enemy is wind. Canyon geography creates what engineers call a venturi effect. Air is forced through a narrow channel and accelerates, like squeezing a river through a bottleneck. The Huajiang Canyon funnels wind into the bridge from specific angles at speeds that can cause a phenomenon called vortex-induced vibration. This is where wind creates rhythmic pressure waves on the bridge deck, and if those waves match the bridge's natural frequency, the whole structure starts to oscillate. You might recognize this from a famous disaster. The Tacoma Narrows Bridge in 1940, which shook itself apart in 64 km/h winds the Huajiang routinely exceeds. To fight this, engineers subjected scale models to hundreds of hours of wind tunnel testing, simulating every possible wind angle, speed, and weather condition. The deck design was refined until it naturally deflected wind rather than trapping it, and the bridge was fitted with aerodynamic stabilizers, fins, and vents built into the structure itself. The second enemy is earthquakes. Guizhou sits near active fault lines. The bridge had to be designed not just to survive an earthquake, but to survive while carrying traffic during one. The solution? Fluid viscous dampers, essentially giant shock absorbers, installed at key connection points throughout the structure. When seismic energy moves through the bridge, these dampers convert it into heat, dissipating the force before it can build into structural failure. It's the same principle as the crumple zones in your car. Controlled energy absorption rather than rigid resistance. The third enemy is the unknown, and this is the one that keeps engineers up at night. Because no matter how good your models are, real-world bridges behave in ways simulations don't always predict. The Huajiang Bridge is embedded with a fiber-optic structural health monitoring system. Thousands of sensors woven throughout the cables, deck, and towers. 24 hours a day, these sensors track stress levels, vibration frequencies, temperature changes, and micro-deformations. The data streams in real time to engineering teams who can detect and respond to any structural irregularity before it becomes a problem. In a sense, the bridge is alive, constantly sensing, constantly reporting. But here's what makes Huajiang genuinely unique in the world of mega infrastructure. It was designed from day one to be 2 things at once: a utilitarian highway crossing and a destination. The bridge features glass-floored walkways along its edges where visitors can look directly down 625 meters into the canyon below. A glass elevator descends along one of the towers, offering a vertical journey that most people describe as, let's say, memorable. And for those who find that insufficient, the Huajiang Bridge hosts bungee jumping, a 625-meter free fall above one of the world's most dramatic natural landscapes. Extreme sports, tourism revenue, international attention, infrastructure that pays for itself in ways that never appear on a construction budget. It's easy to look at the Huajiang Bridge and see just an engineering achievement, a record broken, a technical problem solved. But zoom out, and the picture is far more profound. For the communities on either side of that canyon, this bridge isn't a tourist attraction. It's the first time in history they've been connected. Farmers can reach markets in minutes instead of hours. Students can access schools they couldn't reach before. Medical emergencies that once meant hours of dangerous mountain road travel are now routine transport. One bridge, thousands of changed lives. And Guizhou's 32,000 bridges represent that same story multiplied across an entire province. A systematic, deliberate campaign to rewrite what geography means for human possibility. The Huajiang Bridge cost billions to build. It took years of engineering, thousands of workers, and solutions to problems that had never been solved before. And it will last for over a century, which means the 2-minute crossing that replaced a 2-hour journey will be made by people who haven't been born yet. That's the real ambition here, not a record, not a ribbon cutting. A permanent reshaping of what's possible for the people who live in these mountains. And maybe, a reminder to the rest of the world that the greatest engineering achievements aren't the ones that defy nature. They're the ones that quietly, stubbornly serve people. 625 meters, 2 minutes, one bridge that changed everything. If this kind of story moves you, drop a comment below. Would you bungee jump from the Huajiang Bridge? I genuinely want to know how many of you are actually brave and how many of you just think you are. If you want more deep dives like this, subscribe and hit the bell. Stories about the structures, phenomena, and ideas that quietly reshape our world, that's what we do here. I'll see you in the next one.